Okay, hi, welcome everyone to the session 5. Today we will take forward what we started discussing from the last session, exploratory data analysis. We'll take it forward and discuss some of the advanced topics. And for this, we'll take a new data set and explore through that. So I have also uploaded the worksheet for today's session in the GitHub location. So if you go to GitHub, the ML course V1, so I have created a new folder called session 5, in which I have uploaded the worksheet. Again, we'll go through the live coding today. And I have uploaded the data set called cost data, customer data, which we'll explore through in this session. I will give a minute to download this and upload in the Jupyter notebook, and then you can start the worksheet in the Jupyter notebook, and then we'll get started. So once you're done, just can you say yes or done on the chat window? Okay. So this is a census data set which was taken from the book repository of a book called Practical Data Science with R. Okay, it's a very nice data set. This has also some missing values, so we'll also look at how to deal with missing values today. The data set contains information about customers who had insurance cover for health insurance, and certain other demographic parameters like gender, male or female, whether he or she is currently employed or not, income, what's annual income, marital status, house type where he or she lives, number of vehicles owned, whether moved into the house recently, age, and state of residence. This is, of course, a US data. So it also provides the state of the residence. So what we'll do is we'll go through this data set and explore some of the advanced concepts in exploratory data analysis. We'll take forward what we started with in the last session. So as usual, we'll import the libraries that required, import pandas, and you can also import warnings sometimes, especially if you want to ignore those warnings. You can say import warnings and filter warnings, ignore. So let's read the data set first. So you can say cost data pd.read.csv. So like last time, I will also do the live coding, and then you can either follow along with me or you can watch the video later and try it again. Okay, so let's cost CSV, but this is actually a tab separated data. So we have to actually provide the separator. By default, the separator is comma. So in this case, because the separator is tab character, we have to pass another parameter called separator, and say cost data dot head. Let's look at some of the records in the data set. As you can see, there's also a column called cost ID, customer ID, which may not be, which is not a variable. We don't need that information, but other information like sex or gender, is employed, income, right, marital status, health insurance, whether the particular customer has a health insurance or not, housing type, and so on and so on. And you can also see there are some non values are there, right? So that means there are some values which are missing in this particular column called is employed. So we don't know the particular person is employed or not, right? So there could be some other missing values somewhere else as well. So we'll go and explore that first. But before that, again, let's do some basic metadata exploration, which normally you should do when you load a data. Uh, so how many records? There are about 910 customers with 11 columns. Of course, one of them is customer ID. So the remaining 10 columns are actual information about the customers. And you can also do info, which will show you how many missing values are there. So each employed, there are only 655 data points. Remaining are all missing values. Same thing for housing type. Also, we don't have some information. Recent move and num vehicles, right? But remaining all are available. And as you can see, these are basically your categorical features, right? This is a numerical feature. And health insurance is actually also categorical, but it's a boolean. It's basically yes or no. Okay. So we can observe that there are missing values is employed, housing type, recent move, and num vehicles. We can also visualize the missing values. All right. This will also show if there is a relationship between the missing values or between the columns. And so you can actually import or install a library called missing no, a very interesting library. So if you have not installed, first time you're using, you can uncomment this and say pip install missing no. And once you install, for example, in this case, it says requirement is already satisfied. That means it's already installed. We can import missing no as msno matplotlib, and then we can actually see how many missing values and if there is any relationship between the missing values. So to do that, we can say msno dot matrix, right, cost data. So you can see there are missing values in is employed. If there are white lines are there, those are basically missing values. No values are there. In housing type and recent move and num vehicles, you can see there's a relationship. So whenever there is a housing type is not available, of course recent move will also be not available, and number of vehicles is also not available, right? There is a whenever either all the three columns are available or they are not available. Okay, but each employee is quite significant number of values are missing, whereas in these three columns there aren't many missing, but there are only very few missing, as you can see here. And we can also count how many missing values are there. So you can say cost data is null. So if you say cost data is null, it creates a matrix to denote which all column values are missing. For example, here it's saying it's true. That means this particular value is missing, and false means this is not missing. Okay, you can see wherever it's true, those values are missing. Okay. But of course, we are not interested to exactly look at specific missing values, but overall we're going to look at how many missing values are there or percentage of missing values. So we can say dot sum. So what will happen is the true value will be converted to 1 and false will be 0, and when you sum it, it shows how many missing values are there in each column. As we already seen, is employed, about 255 missing out of 910, right? So almost a quarter data is missing, more than quarter. But whereas housing type, recent move, and num vehicles, they are not missing much. Now you can ask a question. Whenever you see missing values, there could be many reasons why the values are missing. Okay. One could be, of course, data is not available at the time of capturing, so it was not captured. It could be a recording error as well. Okay. Or user might have intentionally not filled the data, right? So when you ask specific information to the user, and probably the user might not have filled because of specific reasons, we'll look at that. So missing data typically can be classified as either of the three following categories. Okay. This is a little confusing, but initially, but it's very important concepts to know. So once you start dealing with missing values multiple times, of course, you will get to know. But just to get an initial idea what missing values are there, one is called missing completely at random, right? Missing at random and missing not at random. So missing completely at random is when you see missing values in a specific column and there is no specific reason why it is missing. So the probability of missing for any particular column and any particular value is same. Okay, this is randomly missing. So this is completely randomly missing. Okay, but missing at random could be the missing values could be for a specific reason. Okay, I mean, one of the examples given by some of the articles is saying, let's say, it may be true, right? So when you ask about the age to a particular gender, let's say female, they typically tend to not fill it. So there could be missing values in age, okay, and those missing values can be actually related with another column, let's say called gender, right? So the values are missing because of certain reason, right? But whatever the missing values, we don't know exactly what the value is. Okay, it's not missing completely at random. It's missing, but the missingness, we call it missingness, is actually related to another variable or column in the data set. And there's something called missing not at random. I mean, to give another example is, there's another example given is saying that, especially when you ask about a specific question, right? Have you gone through depression, right? Typically male not to tend to ignore that question, not answer those questions. Then you can know that, okay, if the value is missing, probably related to a gender again. There could be many specific reasons about it, right? Missing not at random could be the missing values in a particular column, okay, may be related to another column, but there could be a specific reason why this particular column value is missing. For example, let's say in our case, is employed is missing, right? Is employed is missing. Maybe because people who are not employed, they tend not to fill that value. It's not necessarily it is related to any other column. It's very specific to that column itself. People who are not employed typically tend to ignore that question and not fill it, let's say. Okay, so that could be missing not at random. So there's a nice article here if you want to go through it, missing completely at random. So there is no pattern to the actual values of missing data themselves. It's called missing completely at random. Missing at random is missing data, right? Whenever there's missing data, do have actually relationship with other variables in the data set. Like for example, I told you the age could be related to maybe gender. But however, the actual values that are missing are random. So when the age column is missing, so whenever there's a missing value, it could be, let's say, female, right? but what exactly is the age, we don't know, right? It's missing. And if a particular age group or particular age range for females tend to not fill these values, that could be a different reason altogether, right? Same thing, missing at not at random. Uh, Here also is given example like smoking status is not documented in female patients because the doctor was too shy to ask, right? So this could be a correlation here. Why we need to understand that is because um, when you want to deal with the missing values, if you don't know the reason, right, why they are missing, it would be not appropriate to impute very randomly. Okay, because if you impute or deal with missing values very randomly without understanding the underlying context or the reason why they are missing, we might be injecting a lot of noise in the data, right? So whenever you see missing values, try to understand if there is any reason why they are missing, and are the missingness of those variables or columns have any relationship with any other variables in the data set. Okay, that's very important to understand. Okay, so for example, I've given here quite a lot of values are missing is employed column. This may be either because person does not have an active or full-time job, right? Or at the time of capturing, user might not have filled the employment information. It's also possible that we can also estimate this based on the income level. If the income level is beyond a threshold value, below a threshold value, so it's probably, you can say, okay, this person probably is not employed. Now, how do we deal with missing values? There are multiple steps that can be taken. One is obtain the missing data. Okay, so this is actually go back to the data collection again. Okay, and obtain that. So this probably is wrongly missing, primarily because of you designed a data pipeline, right, which brings data from the sources and create a data set, but there is a bug in the pipeline, or there is a mistake in the pipeline because of it's missing, so you go back and collect data again. Okay, or you do a survey again, right, to capture those information, but this is a little hard work. Okay, this will actually involve extra cost and effort to obtain those missing values. Leave out the incomplete cases and use only those which all variables are available. So one way to basically drop all those data points or samples where missing values are there. Okay. Replace missing data with a conservative estimate, right? So you can actually, this is also called data imputation. So you can fill those values with a default value, right? Or you can fill those values with a estimated parameter, like a mean imputation we call it, or a median imputation. We'll look at some of the topics today. Or estimate the missing data from other data on the person, right? So one is, of course, if there's a particular column there in the data set, let's say there's a data set with x1 column, x2 column, and x3 column. One base, let's say there are specific values which are missing, right? Let's say this value is missing. Then what you can do is you can impute this with the mean value of the remaining all available values of the x2. So you can calculate x2 mean and then replace this. The other one is estimate the missing data from the other data. For example, let's say x2 has a relationship with x1 and x3. Then you can actually estimate the value of x2 here with whatever the remaining values are there. So you can actually build a function that can estimate the value of x2 from x1 and x3. Okay, this is also called a model-based imputation. This is called what? Model-based imputation. So there are 4 different ways. One is go and collect it, drop it, right? Do a simple imputation by estimating a parameter or conservative estimate of a parameter like a mean median, or you build a model to estimate the missing values. Now question is how much missing value is accepted, right? So if you have a data set where one of the column has too many missing values, right? So typical thumb rule, of course, this could be very specific to different context as well. But typically if more than 20% data is missing, there's too much is missing, right? And when you impute it, you're imputing with too many imputing too many missing values, so the amount of noise that you're injecting data is too high, right? So normally you don't do that, but this 20% could be very context specific, right? You would understand from the domain. In certain domains, missing values cannot be imputed. You can think like a healthcare, right? You really cannot impute the if a specific value is missing, like a blood count or heart rate or whatever, right? Simply you cannot do that because imputation can lead to high risk. It can inject unnecessary noise into the data. So typically in certain cases when missing values are there, just dropping the data from the data set is a good idea, right? So I need to understand all this context, right, to do the missing value imputations. Now coming to drop samples with missing values. Okay, in case you have to drop the values on the missing values, so it's as simple as saying, let's say it's a customer clean data equal to cost data, drop NA, right? What this is going to do is going to now if you look at the SAFE, there's only 647 records are there because other records have some of the missing values. And if you look at the missing NO matrix on the custom clean, now you can see that nothing is missing here, but a lot of data points are actually dropped here in this case, right? So drop if values are missing from specific columns. So in certain cases what might happen is, so let me probably show it here. So drop NA, there are multiple different strategies you can apply to drop also, not necessarily blindly dropping it, right? So let's say there is a data set where there are 4 columns are there, x1, x2, x3 and x4, and let's say there are 5 samples are there, s1, s2, s3, s4 and s5. Let's say in this sample x2 is missing, in this sample x3 is missing, right? And let's say in this case these 2 are missing, and so on and so forth, right? Now if you say let's say this is the data frame df. Now if you say df dot drop, right, so it will only select s1, s2 and s5 because these are only records where none of them missing values, because other records have missing values, so those will be dropped completely. But let's say from your analysis you found that when x3 is missing, it can be dropped because x3 is a very important sensitive information, okay, and which cannot be imputed at all, right? That will inject a lot of noise. So you say that you only drop the records if values from x3 is missing, but other columns missing values are fine, okay? Just give an example, right? So then what you can say is you can say df dot drop, right? So in the drop there is something called a subset strategy, right? So you can basically say x3. So you can specifically say if there are missing values in x3, only then you can drop it, right? So in this case what will happen is only the records, right, where x3 value is missing we dropped. So here s1, s2, s4 and s5 would be selected, but s3 would be dropped. Or you can also do some complex dropping strategy. For example, let's say um, in cases of let me this. Yeah. So let's say you say that x2 and x4, right? If there are missing values in any of these two, right, then it's fine. But when both are missing, it might be possible that when there is a value in x2 is missing, I can impute from x4, or when there's x4 is missing and impute from x2. But when both are missing, this cannot be utilized. So this can be dropped. Then you can say drop, right? Subset, right? Drop subset strategy is x2 and x4, right? And then basically there is a option called all, right? It's saying that when all the values in these two columns are missing, then it can be dropped. But if any of them are available, you can retain them. So in this case, only S4 will be dropped, but other values can be retained. Okay. So the dropping mechanism is quite complex, but it can be leveraged based on your understanding of the data and what can be retained and what can be dropped from the data set. Understood? So let me show that little. In the documentation, you can actually look at it. So pandas drop NA strategy. You can see the subset, the drop NA, there's a subset column and there's a how column, right? In the subset, the column labels, the sequence labels along the, if you're dropping rows, this would be the list of columns to include. Okay. How is basically look at any or all, right? If any of the values are missing or all the values are missing, it can be done. Okay, but of course we don't need the strategy here, so we will not be adopting that, but that's a something very important thing that you must be aware of. So drop if values are missing from specific columns. Maybe we'll just try one more, right? You can basically say, again, cost clean equal to cost data drop NA. You can say subset, right? Let's say it's a num vehicles. Right? So you drop the record when the number of vehicles is not available, right? And then you can see the cost clean, and we can see maybe the shape of it, and quite a few are retained. Only the values where the cost num vehicles are missing are dropped, right? But the values where the each employed is missing is not dropped from the data set. Okay. Now let's look at, this is of course how to drop. Now let's look at the imputation techniques, right? So like you can impute with the default values, you can impute with estimated values, or you can also build models to impute those values. So for default values, for example, let's say from your understanding, you say that each employed is missing means those people are not employed. Okay, that's our understanding. Then you can say cost data, right? Each employed, right? Imputed. I'm creating a new column. I'll tell you why. Then the cost data each employed, right? Then you can have an option called fill NA. right? So whenever there's a non values are there in is employed, we can say set to false. False means they are not employed. So if you look at the cost data now, head. So whenever there's a is employed missing none, I've set to false here. Of course, when there is a missing, not missing, it's of course retain the same value. And whenever you are imputing, it's not a good idea to overwrite the original column. Okay? You always create a new column in which the missing values are imputed. Okay, so that later when you do analysis, okay, you can still have the data to figure out which were missing and which were imputed, and you know based on that you can also understand how those imputations are impacting the model building and all that, right? So it's always a good idea to retain the original column and create a new column saying that imputed from this particular column. So this is of course imputing with a default value. Wherever values are missing, just say they are not employed. Or you can also do based on a particular condition. For example, you can impute based on some other parameters, right? Now let's say, just for example, I'm saying that if the income level is below a certain threshold value, maybe we can impute only those missing values as a not employed. But if the user has not entered the value for the is employed, but the income is very high, maybe they are employed, they just forgot to or not fill those data. Okay, but to do that, first we need to understand how income and is employed from the existing data, when they're not missing, how they are related, right? So what I can do is you can compare the income distribution of all the three different groups. One is those who are employed, right? Those who are employed, what's the income distribution? Those who are not employed, we can look at that distribution. And there, when there is a missing value, what's the distribution, right? We can compare and see how they relate to each other. So what I can do is you can create three different groups. Let's say I'll say income of those people who are employed, right? Customer data, and age employed, right, equal to true, right? That means these are people who are employed, and what is their income. So I'll go to store in a variable called the income employed. Now let's say I will also create something called income not employed, and this will be equal to false, right? So the two groups now, the income of those people who are employed, income of those people who are not employed, and the third one will be what? The income of those values that the missing employed value is missing, right? And this would be basically, you can say, is null, right? So when the is employed is null, what's income? So that three different set of values now. And then what you can do is you can go and compare the distribution of it. So if you remember, we've done the distribution before. Either you can do a box plot, or you can do also the KDE plot to compare the distributions. So let's say do plot figure, fig size, let's say we'll keep to the default 12 and 6, and then say KDE plot for income employed, right, and income not employed, and then income missing. And of course we don't know which one belongs to who, So we have to go and add what? Level, saying that okay, these are for people who are employed and these are not employed and these are missing. And we'll create a legend to observe that. So if you see here, now there are three different distributions, income distributions. The blue one belongs to the people who are employed, and you can see it's a right shift distribution. So typically people have a higher income, okay, seems to be all employed, or the other way around, people are employed typically have a higher income, but people who are not employed and missing, okay, there seems to be a very similar distribution if you look at the green and the orange one, right? The average is about here, okay, the income, whereas this is probably somewhere around here, right? So the initial inference could be people who are whose values are missing in the age employed, they have income very very similar to people who are not employed, right? So we'll go to little more verification. Always you have to go understand little deeply. We can do hypothesis test. That means we can say, is the average income of those people who are uh, missing, that means the employed value is missing, is the same as the average income of those people who are not employed. Okay. So if you remember, we can do a simple t-test here. Let's say SciPy import stats, right? Just to compare, is the average income of those who are not employed is very similar or no, same as the average income people whose employment information is missing. Right? So you can say stats dot t-test independent, and then compare income of those not employed and income of those what missing. So here you can see the p-value is more than 0.05, right? More than 0.05. So you can have the conclusion or some inference here saying that the average age of those people who are not employed is the same as the average income of those people whose employment information is missing. So this can lead to a conclusion. Of course, we may have to maybe look at little more information that whenever the missing value is there, typically it means they are not employed. And if you go and compare also the average income of those people who are employed and missing, right, you can see the p-value is very small. That means the average income of those employed and missing are very different in this case. Okay. So in a way, what I can do is we can conclude saying that okay, people who whose income level, right, is the income level of those who are not employed, we can impute them with the missing values. So here what you can do is you can calculate the average value. The two ways you can deal with this, right? One is of course all those who are missing here, all those who are missing, you can directly now set it to not employed. Okay. Or you can also do something, right? The income not employed, you can calculate the average value and say, okay, if the income is less than that average value, you can set to missing. So you can not employed. Okay. Or if it's more than average, then you can say they are employed. You can also adopt that strategy. So I'll just show you how to do that. So let's calculate the average income of those people who are not employed, mean value. So I think the average income is about $23,000. And now in the missing values, if anybody's income is less than that, we can say that they are not employed, and more than that, probably can say they're employed. Okay. So both the strategies we can do. I'll just show you how to do that. You can say customer data is employed imputed to. I'm writing 2 because we have already applied one imputation technique. Of course, in the real world, you will only adopt one of the imputations, but I'm showing here different ways you can impute, right? And I'm just using a different variable to store that information here. And so you can say equal to customer data. So what we'll do is we'll look at the income value. Right, map lambda you can say false if x is less than the average income, else true. But this will also do a little bit of mistakes here. Of course, I will ask you to fix this in your assignment, okay, because this is also looking at the income of all the customers, but I need to look at the income of only those people whose employment information is missing. Okay, we need to look at that as only. If so condition based imputation also you can do, okay, but of course for that you need to understand some of the relationship missingness with other variables. In this case we looked at income. Okay, now let's look at another column called number of vehicles. So you know that there are some values missing in the number of vehicles also, right? So here you can say again can assume that people who have not entered number of vehicles, typically people who do not have vehicles, right? So you can simply say cost data num vehicles, right? Impute 1, give me a second. So cost data num dot fill in a 0.0, right? So basically saying that okay, people who have not filled, probably they don't have vehicles, so you can just simply say 0. Or you can also do a parameter based estimation like a mean value imputation. You can say okay, calculate the mean value of all those people and we'll just impute with the mean values. So to do the mean value imputation, so let me write it mean based imputation. So to do this, there are libraries which actually has an inbuilt features to do that. Okay, there are specific regions. Of course, we'll come and discuss when to apply imputation, whether to apply imputation on the complete data set or only a subset of the data. That will of course we'll discuss later when we come to building models. Okay, and we'll understand what is the implication of imputing the complete data set or the only trained data set or test data set. Okay, we'll understand that later, but just for the timing we'll just see the complete data set and do a mean based imputation. So you can say from sklearn, so scikit-learn, which of course we will explore in very detail when you come to model building, but for the timing I'll just show you one example of how to do a mean based imputation, or in this case I think I'm going to do most frequent based imputation. I'll tell you what. So what I'll do is, there are some people who have number of vehicle 0, number of vehicle 1, number of vehicle 2 and 3, right? So what we'll do is, we'll look at how many people have 0 number of vehicles and how many have 1, how many 2 and how many 3. What are the most frequent? Okay, so we'll actually impute with that particular value. In this case, not calculate the mean value, we'll actually do a most frequent based imputation here in this case, because if the number of vehicle is a discrete value, calculating mean probably will not make sense here at all. So mean value typically can calculate when you have a continuous value. I think I have specified that here, somewhere here. The imputation estimated values, numerical features, especially when you have continuous values, you can do mean or median based imputation. Categorical features, you can do most frequent, but you can also apply the same thing for discrete values as well. So once you import simple imputer, now you will initialize the simple imputer, and here in simple imputer there is again an option called strategy, right? So if you look at the documentation of simple imputer, the strategy, there are multiple different strategies are there. So if you say mean, then replace the missing values with the mean value of the remaining non-missing values, whatever they calculate for each column. If median, replace the value with the median value. Most frequent means the replace the missing value with the most frequent value along the column. Or you can also do a constant, the constant value. With this is almost same as your fill NA, right? You can also use this particular strategy and this API instead of fill NA. So all these 4 different strategies are there. So here let's say I will call it a strategy equal to most frequent, and I'll come to specify that what it basically means by add indicator. Add indicator means it's going to, let's say in a data set there is a missing value x1, x2. Let's say you are applying the missing values there in x2, you are applying most frequent imputation. So it's going to create a new column called whatever x2 impute, and is also going to create a separate column to specify which actually the values are imputed, like an indicator. So okay, this value is not imputed because it's already there. This value is imputed because there is a missing value. So along with the applying imputation and creating a new column, it's also going to create an indicator column. Okay, this is very important from the error analysis perspective. So when you do error analysis, when you build a model building, you can go and observe how your imputation have actually affected the error. Or sometimes even this column can also be provided to the model to understand, you know, which values are missing. Okay, so that could be an additional information that can be passed to the model. So it's always a good idea to create an indicator column when there are missing value imputations done. So now we don't, there's a question called, should we not change the name of the variable?
We're calling it mean imputer, but we are doing most frequent. The strategy should be, no, in the next, yeah, this, if we're not doing mean, then why should we call it most frequent? On the left hand side.
Yeah, okay. Yeah. Yeah, that makes sense. Yeah, just the name. Yeah, it's good to have a the correct name. Correct. Most frequent. Thank you. Then we'll actually num vehicles imputed. So you can say most frequent imputer fit and transform. Okay. Typically, you should call fit and then transform, but we'll come to that aspect when you actually go to the advanced topic. But as of now, I'll just do fit and transform at the same time. So in this case, what we'll do is going to first calculate the frequency of each of the unique values in the number of vehicles, and then impute with the most frequent one. Okay, now if you see the num vehicles imputed, okay, it's going to create two columns now. So this is the column, the first column, which is it contains the imputation values also. So values were available, of course they'll not be imputed, but when the values are missing, it will be imputed, and it will be actually an indicator column saying 0 and 1. Of course, it's not showing all the values. So let's do one thing. We'll just add to the original data set, and then we'll look at that. So now customer data, we can say num vehicles impute 2, right? We'll take this first column here. Okay. So this is an array. So this particular notation means you take all the rows and the first column and add to the customer data as the imputed values for the num vehicles. Okay. And then you take the second column, right? Second column as just an indicator. You add to the original data set. And then if you look at the values now, for example, let's look at the original, what the values are. Then this two. So this is the original values, num vehicles. This is the imputed column now, and this is the indicator column, right? All the three. And then what you can do is we can let's break this. Okay. Dot sample remain, just simply sample it. Let's say just want to sample a specific rows, so you can see that here, right? So the number of vehicles, when it's of course available, it's kept same as it is. When there's a missing value, it was actually replaced with the most frequent one. There's an indicator also got added here saying that this particular value has been imputed. Okay, in this case looks like 2 is the most frequent, that's why the frequency is very high for 2, so it has chosen 2 to impute the value. Okay, but whether this approach is correct or not correct, for your data set and the context, you need to understand very deeply. Okay, analyze it and then apply this. Okay, but once you decide to apply, you can apply this particular strategy like this. Okay, so normally we will be using the scikit-learn API to impute values rather than doing uh, the pandas API. Okay, so there is also called model based imputation. Okay. So in this case, we'll actually build a model. Like I told you, if x1 is missing and can be imputed from x2 to x3, we can actually go and build a model based imputation, x2 and x3. And one of the most popular model based imputation is called KNN imputation. Now, because we have not understood KNN, what is KNN and all that, we will discuss this later when you come to the modeling part. We will of course understand in detail what is KNN, and then we will actually utilize that to do imputation as well. Okay, so for example, you can say the number of vehicles missing could be estimated from what is your income, what is your age, and what is your housing type. Let's say these three values can actually, estimate how many vehicles you own to a certain extent. Then you can actually build a model called num vehicles, right? Num vehicles equal to as a function of income, age, and housing type, right? You can actually do that, but I'll skip that for the timing. And when we come to uh, the modeling part of it, once we understand Canaan, we'll look at that in detail, right? Again, when to apply imputation, during the EDA process, or you just understand how the values are missing and what can be imputed, what cannot be imputed, what kind of imputation can be applied, and they defer the actual imputation to the, pre processing pipeline of the model building itself. Okay, so we'll look at that in detail when we come to that. So quickly, we understood now how to figure out what values are missing, how much are missing, right? If the missingness has any relationship with any other variable, or it's randomly missing, right? And whether it can be imputed based on different strategies, the default value, mean or median or most frequent, or model based imputation. Okay. Now, what I'll do is we'll do some exploration now from the data set perspective. So if you see the original data, cost data, if you look at the head, right? So this data set is also a wonderful data set to kind of build a model to, generate leads. Let's say there's a company, the insurance company, who's tried to sell insurance product, health insurance product to customers. So you actually can build a model to understand what is the likelihood a customer will actually buy a health insurance coverage or not buy a health insurance coverage, right? By leveraging other information like what's a gender, what's an income, is currently employed, does have a house, what's the age, and so on and so forth, right? So what I'll do is we'll try to see the relationship of all these variables with the insurance. For example, gender versus insurance. Okay, typically the number of people who buy insurance, do we see a difference in frequency or probability distribution between two different genders? For example, male and female, right? So what you can do is, in this case, we can do a remember in the last EDA also we discussed about things like if two are categorical features. So in this case, gender is a categorical feature, and insurance, right? In this case, health insurance is also a categorical feature. So what you can do is you can, in this case, either use a bar plot, right? Or you can use a cross tabulation, PD cross tabulation, right? So let's look at that. So you can say PD cross tab, cost data dot sex, this is basically the gender column, and cost data health insurance. Because this column has a dot in the name, we cannot use like a typical variable. Okay, it always has to be written like an index here. And then we say normalize, right, by index in this case. You can see of all the females, the number of people who have actually has health insurance about 90%, only 10% don't have it. And the male about 85% who has it, and 14% do not have it. there seems to be not much of a difference, okay, in the probability distribution. Okay, so both the genders have the distribution of whether they have health insurance or do not have health insurance are very similar here, which of course you can also depict like this in the bar plot. Let's say sn dot count plot. Remember we did a count plot last time. We can say cost data. Your x will be in this case gender, let's say sex, and y would be health insurance. Let's see. Not y. This will be hue. Third category, right? So x is sex, y is always count, so you cannot change that. In the count plot, the y is always count. So first male and female, and then within male and female, the further subgroup can be done with the health insurance. So you can see there are of course more number of observations in the male compared to female, but in terms of proportionate between the number of females who has insurance and do not have it, and the male who has it or do not have it, seems to be very same. Okay, what is of course we have observed here. So when you dealing try to find the relationship between two categorical features, these are two important ways we can do exploration and look at the relationship. Now let's look at is there a difference in income distribution between different state of residences, right? For example, do you see the income of a particular state is higher compared to the income of different state? Typically it would be higher and lower, but then how they are distributed, let's say you want to look at that. Then what you can do is you can but let's first look at cost data. How many states are there? State of residence. Let's look at unique values. Key error RES, only RES. Okay, so of course quite a significant number of states are there. If you look at all 49 states are there. So that will be very clumsy if you look at all the states. So what we'll do is we will only look at the states, the top states whose incomes are very high, and then compare the distribution. So to do that, what we can do is we can maybe select top 10 states by the median income value. So you can say cost data. Remember we did this last time also, group by state of residence, and then we look at the income value, right? So we'll group all the income by different states and then calculate the median value. Okay, and we can do a reset index to return the results in terms of data frame. So the median income of Alabama is about $22,000. Alaska is $33,000. You can see some states are much higher, $64,000 and $94,000. But some states are very low, like $8,000 and so on and so forth. These are of course not about all the residences in that state. The people who are basically customer of this particular company, right? Who are basically customers who has health insurance and do not have health insurance yet. Okay. So what I can do is you can store this maybe to a variable income by state, and what we'll do is we'll only select, we'll first sort the values by the income. All right, ascending equal to false, and look at the top 10. right? So these are top 10 states. So Delaware is $94,000 average. It's very high actually. Right? And then we will only do a distribution comparison of these 10 states. So here in this case, we will, let's say, top 10 states, and we'll only select the name of the states here. Okay. So top 10 state names. So they are top 10 state names. And now what we'll do is we'll compare the income distribution for only these specific states. And how do you compare the income distribution across the states? Again, income is a numerical feature here, and state of residence is a categorical feature. So when you have a numerical feature and a categorical feature, we can do a box plot by categories, right? We can do box plots by categories. So in the last session, I have given the rules. We can apply those rules now. We can say sn dot box plot and data equal to cost data, x equal to what? State of residence. So on the x-axis, I want to see different states, or you can also look at on the y-axis also. So let's change it to y. We'll do a different orientation now today, just to a little different than compared to last time. Your x will be income, and there is a variable called orient. Okay, once you see the picture, you will actually get to know. And then order by the state names. Okay, let's little change the size of the plot. Maybe a little more. Yeah. Okay. This looks good. So here my x is in y is state of residence. So you can Delaware, Nevada, Idaho, Hawaii, and all that. Then x is income, right? Value which ranges from 0 to almost 400,000. And then orient is horizontal. You see the box plots are horizontally aligned now. We can also do vertically aligned. Okay. And we are only looking at the top 10 ones. So it is selected only the top 10 ones. And you can see the income median, this is a median income, and there's a variance in the data. So there are some outliers here, this particular specific states. Okay, so this is a very long tail, right tail distribution for mean, and so on and so forth, right? This, of course, we're looking at the top 10 ones. You can randomly also select and look at the distribution of that. Okay, now let's look at a few more. State of residence versus housing type. So what is housing type? Cost data, let's say what is housing type? Unique values. So people who have houses, that they're categorized into two different categories. Sorry, four different categories. One is called homeowner, free and clear. That means they own a home without any mortgage, completely free and clear. One, those who rented the place, they don't own it. Then the people who are occupied with no rent, not sure why, but there's also a category who are staying in a place without paying any rent. And then the people who are owners of the house, but currently they're paying a loan or a mortgage, right? So the four different categories are there. So now let's look at if different states have a different distribution of these four categories, right? So again, in this case, we're talking about a categorical feature and a categorical feature, both a categorical feature. So you can do a cross tabulation and put that into a heat map. If you remember that heat map we did last time. So let's say, again, in this case, we will not look at all the states. We'll again look at the top 10 states. So we'll only select the top 10 states info, right? Top 10 states housing types, and the cost data, state of residence is in this particular list. For the time, we'll just compare this. So what it'll do is basically it's going to select only the records where the state of residence is actually in this particular list of 10 states, and then we'll do a cross tabulation, right, between these values. The top 10 housing state of residence and top 10 states housing type, right? And do a normalize by index. Okay, so this is the distribution of different states. That means in Arkansas, people who are the customers from this particular state, 60% people are with a homeowner mortgage, and homeowner 40% remaining free and clear. And interestingly, none of them are rented or occupied without rent. Okay, whereas in certain states, 50% people are basically unrented, and nobody owns a home with a free and clear without loan. So you can see the distributions are very different. But again, this can be better visualized using what? If you remember, a heat map, right? Very interesting plot which can show this pattern very nicely. So you can see sn dot heat map. Housing by state, and annotation equal to true, right? So this is and what you can do is you can also change the color a little bit. Normally I like this color. BU, is it? Yeah. Okay. So you can see these two states, Delaware and Hawaii. I think 100% is people with the mortgage and loan, whereas occupied with no rent is almost no other states have except New Mexico. People who are occupying without any paying any rent. Whereas in rented, I think 50% people in Rhode Island is 50%, and yeah, there are places where people do not own a home with without a loan, like for example Rhode Island, New Mexico, Hawaii, and Delaware. Right, very interesting pattern here, observations. Okay, I think we have 2 or 3 more to go. Quickly we'll look at that. Age versus income. Now age is what? Numerical feature, income is our numerical feature. So when both are numerical, we can actually apply something called what? Scatter plot, right? So let's look at a scatter plot. So sn dot scatter plot, cost data, x equal to age, y equal to income. Let's change this to small. Yeah. So on the x-axis age and y is income, and if you see, there is no clear positive or negative correlation here, right? You can see on the both the ends, the income is little lower and the middle little higher, right? This makes sense because people who are very young people, probably they don't have much of income, and of course people who are old and retired maybe have a lesser income, but people who are young and mid-aged, people who are actually working, may have a higher income. Okay, so normally what we see correlation is mostly in some of the previous examples. For example, let's say in terms of mileage, right? uh, and price, resale price of a car, we saw a positive correlation, right? And in another example where kilometer driven uh, and price, right, we saw a negative correlation, right? So these are, they basically uh, they're either increasing or decreasing, right? So these are called monotonic relationship. They're called monotonic, right? That means as one variable changes, the other variable changes in the same direction all the time, either positively or negatively, right? But this does not seems to be a monotonic relationship. This seems to be increasing and then again decreasing. They're called non-monotonic relationship, right? It increases until this particular age and then reduces again. Especially when you find a variable like this, which has this impact, it may make sense to convert this variable numerical feature into a categorical feature. Okay, so sometimes a numerical feature can also be converted into a categorical feature. For example, in this case, we can say groups. For example, let's say we can say young people, adult, mid-aged, old people, and so on and so forth, right? And this is also called what? Data binning. This is also called what? Data binning. So let's see how do data binning. Sometimes a continuous variable may need to be binned into categories. For example, age, right? Or for example, income also, low income, middle income, and high income, right? You can actually bin them. So how do we actually bin it? This of course you have to understand, there are quite a few strategies are there. Some more advanced strategies, we are going to do it later. But I'll tell you one simple, of course, based on the domain understanding or intuition, you can say, okay, you can create the bin edges, right? The boundaries of the bins. You can say people who are between 0 to 18, 18 to 35, 35 to let's say, 55, and 55 to let's say 128. I'm writing 128 because there are some people with that age there in the data set, right? And I will say the group names. Now you have to map it the group names. So there are 5 values are there. So each pair you have to find a group name here. So 0 to 18, let's say I will call it young. Okay. So there is of course a mechanism to even find out how many bins should be created and all that. But that's an advanced topic. I'll defer that to later session. I'll just show the basic one here. Mid-age and old. Right. So there are 4 groups here, right? 0 to 18, 18 to 35, 35 to 55, and 55 and so on and so forth, right? 120. And then what I can do is I can say and create a new column now, saying that let's say age group, okay, from the existing age column. So there is a function called pd cut. Okay, it's going to create categories, custom data on age column, right? So cut this age column into bins. Okay, so these are the bins based on these bins, and name them as we call levels. Name them based on this age groups. Sorry, group names. So now if you look at customer data. Okay, let's look at age and age group. Let's quickly sample some, right? And you can see it's a 49-year-old, so it has put that into mid-age, 61 old, 28 is adult, and so on and so forth, right? So now what we're going to do, you can use this variable to understand. Let's say we understand now the income and age group based on this. So rather than income and age, we'll look at what's the relations between income and age group itself. Of course, we now income is numerical and age group is categorical. We can again use what? An SN box plot to do that. So cost data, data equal to cost data, X equal to age group, and Y equal to income. Okay. So you can see that here now, very beautiful depicted here. The young people are very low income, less than 18-year-old. Of course, they don't typically have a mean to income. But adult, you can see increased. Mid-age, the median again increases, but again see old starts decreasing here, right? Maybe you can, if you create some more groups, probably it will be much more systematically shown. But in the four groups, I think that it's increasing the mean, median, and then reducing in the distribution. Okay, so there was a question called how to read the box plot for the Delaware. Okay, so Delaware is only showing one single line here. That means, of course, not much data here, probably Delaware, and most of the data that is there, right, typically looks like all the incomes for the customers who are in the Delaware are around the median only. Okay, so if you look at the distribution sometimes may look like this, right? It's a higher variance, but here it looks like the distribution looks something like this, right? So most of the data are kind of concentrated in the median range only. So there aren't many. The variance is very low, extremely low, right? Variance is extremely low. This might happen because of two reasons. One is, of course, the variance itself is low, or very few data points are there, right? So there are not much variance. So in this, to read a plot, you always look at the box plots into four different regions, isn't it? This is the first 25%, second 25, third 25, and fourth 25. Right. So you can see here the third and fourth are almost same. So the third quantile is very long, right? So this distribution might look something like this. If you distribute this here, this might look something like this. Okay. So I think this brings us to the end of today's session. What I wanted to cover, we have kind of in this two different EDS sessions, we have looked at comprehensively to different data sets. One is the prediction, the resale price of a car, and here, of course, subscription to health insurance, right? And through that, of course, we understood especially how to look at different variables. We looked at the univariate, how to look at each variable independently. We looked at bivariate. Okay, so sometimes we look at multiple different variables also, right? Three variables also, and we also today looked at some of the key concepts of missing values, how to convert a variable from one type to the other type, and when to do that, right? So this kind of completes the the foundations of EDA, and from next session onwards we will start moving into some basic model building. Okay, given that you have done it. As far as assignment is concerned, for this week's assignment, because we have gone through comprehensively, all the steps in EDA, you can pick up a data set, right, from different sources. There are two couple of sources which are very, very popular. One is, of course, we can go and look at UCI, which is called UCI Machine Learning Repository. To search for UCI Machine Learning Repository, which takes you to University of California, Irvine. And you can pick up any data set which interests you. Right, there are about 600 assets are there. And then you can do some exploration, right? Define your own questions, look at the missing values, define the insights, and look at the variables that you're comparing, and do that, and then create those explorations. Now, if all of you create different explorations, then you can share and learn from each other as well. Okay, so again, thank you for joining today's session.